And hi, everyone. Thanks for coming to this webinar. I'm Alden, and I'm a health economist who also does a bit of econometrics. Currently, I'm working on a couple of projects on nursing homes, specifically information frictions that residents face when they are choosing their nursing homes, as well as racial segregation and disparities across nursing homes. I'm also involved in a couple of preliminary projects studying peer effects in health behavior and the causal effects of pollution on cancer. But today, I'm giving an applied econometrics talk. Specifically, I'm going to talk about an empirical method that holds great promise in health research, but that has been arguably been underutilized, multi-dimensional regression discontinuity designs. So let me start off by talking about single-dimensional regression discontinuity, or RD designs, to make sure that we are all on the same page. I'll then describe its extension to multiple dimensions, which will be the main topic of this talk. So the RD design is one of the most promising tools that has emerged from the credibility revolution, which is a movement in economics to develop empirical methods that will allow us to study causal relationships. Of course, the gold standard for studying causal relationships is RCTs, but this is often infeasible, either because we want to study the effects of a past program or because an experiment is unethical. So, out of the numerous methods that have been developed in the credibility revolution, RD designs are arguably the most transparent and also best mimics an RCT. As an example of how RD designs work, suppose we are interested in studying the effects of college going on long-run health outcomes. Now, we can run a regression of health on college going, controlling for a bunch of characteristics, but we may still be worried about omitted variables bias. Now, suppose that there is a college admissions exam and students are admitted into college if and only if their test scores passes a threshold. In this case, if we assume that students cannot precisely control their test scores, then if we compare the outcomes of students who barely passed versus barely missed, the difference is likely to give us the causal effects of college on outcomes. And this is because students on either side of this threshold are quite similar, both on observables and unobservables. So this is the essence behind how RD designs work. Now I'll describe RD more formally and also introduce some notation and terminology. We have a treatment variable Wi, and we are interested in its effects on an outcome Yi. I'll use the usual potential outcomes notation, Y1 and Y0, which respectively describe the outcomes of an individual if she's treated and if she is not. Now, we only ever see one of these, specifically Y1 if the individual is treated and Y0 if she's not treated. So even though the difference is the treatment effects that we're interested in, we can't really estimate it at the individual level. Now, the key points in RD designs is that we have a running variable xi, which has an effect on individuals' treatments. So in a sharp RD design, I'll assume that an individual is treated if and only if the running variable exceeds 0. So this is without loss of generality. If the threshold is some value other than 0, we can always redefine the running variable by subtracting off this threshold value. And suppose that treatment is assigned to individuals whose running variable is below a threshold. In that case, we can simply take we can multiply the running variable by -1, and we will return to this case. So in a sharp RD design, the treatment effect is given by the difference in the conditional expectation functions of outcomes on the running variable as we approach the threshold from the positive side and the negative side. There are also things called fuzzy RD designs, in which case crossing the threshold doesn't change the probability of treatment from 0 to 1, but by a smaller value. And in that case, we can estimate the treatment effects by dividing the difference in the conditional expectation functions, or CEFs, by the change in the probability of treatment as individuals pass the threshold. So this looks a lot like the Wald ratio from IV estimation. So here's a visual illustration of a short RD design. The dotted vertical line is the threshold, and I have plotted in the solid curves the conditional expectation function of the outcomes on the running variable. And we see that as we cross the threshold, the conditional expectation function jumps. And this vertical distance here is our estimates of the treatment effect. So how do we know that the RD design is quote unquote valid? So the most primitive assumption that we need is that the conditional expectation functions of potential outcomes are continuous at the threshold. So if we go back to this figure here, this left curve is actually coincides with the conditional expectation function of y0 as a function of x, the running variable. And what we really want to know is whether if we cross the threshold, this CEF of y0 evolves continuously. And similarly, we would hope that the CEF of y1 also evolves continuously as we extend across the threshold. The problem with this assumption is that it's fundamentally untestable because we never see y1 for individuals below the threshold, and we never see y0 for individuals to the right of the threshold. So David Lee provided a set of more easily interpretable sets of conditions for RDs in his 2008 paper. Specifically, he assumes that individuals should not be able to precisely manipulate their running variable. So I should probably elaborate on this, and the word precisely is actually quite important in the setting. So if we go back to the example of students going to college or taking an exam to determine whether they can go to college, it is okay if some students really want to go to college, and because of that, they study much harder than usual. What we are not allowing with this assumption is that students are able to precisely choose to exert like the exact amounts of effort so that their test score just exactly meets the threshold. That is the kind of manipulation that we are not allowing for. And in many settings, that seems quite plausible. So how do we test whether this assumption is likely to hold? The first way we can test this is using something called the McCrary test. So basically, we are testing whether the density of the running variable is continuous at the threshold. A second test is to conduct quote-unquote placebo RDs. So basically, we are running an RD design, but instead of the actual outcome variable, we replace that with baseline characteristics of individuals. And if the RD design is valid, we should expect the estimated effects to be 0. So this is basically testing whether there is sorting at the threshold based on observables. Okay, so there are many applications of RD designs in healthcare. David Card and co-authors have a paper on does Medicare save lives? So Medicare is probably the largest entrance program in the US, and eligibility depends primarily on whether age exceeds 65. So in this case, the running variable is age, and the threshold is 65. As a second example, there is this paper by Elma et al. On whether medical expenditure improves at-risk newborns' health or additional medical expenditure. So in this setting, they use this fact that newborns are classified as very low birth weight if their birth weight falls below 1,500 grams. And if newborns are classified as such, they tend to receive more medical treatments. So in this case, the running variable is birth weight, and the threshold is 1,500 grams. The final example is another paper by Elma et al., who studies the effects of longer hospital stays for the outcomes of mothers and newborns. They use the institutional fact that hospitals are reimbursed based on how many midnights newborns stay. So as a result of this, as a result of the way entrance is reimbursed, newborns that are born just before midnight stay longer on average than those born just before. In this case, the running variable is the clock time of birth, and the threshold is midnight. There are many other applications, but I'll skip them in the interest of time. Now, I've talked a lot about the advantages of RD designs, and the biggest of which is its transparency and clean identification. But it has one big limitation in that it only estimates the effects of individuals with running variables that are close to the threshold. So let's now suppose that there's actually heterogeneous treatment effects. And we can also think that the treatment effects may depend on the running variable. So perhaps the treatment effects is larger for individuals with higher values of the treatment variable or vice versa. And that's why I define this object tau of x, which is the treatment variable for individuals with running variable value equal to x. The RD design only identifies the treatment effects for individuals at the threshold, that is tau 0. Now, there are other quantities that we may be interested in, such as average treatment effects. So that's basically the integral of tau of x over the distribution of x. But we can't really investigate that using an RD design. A second thing we might be interested in is treatment effects heterogeneity. So how does the treatment effects behavior effects? This first point, the average treatment effects, can't really be addressed using RD. But the second one, treatment effects heterogeneity, we will actually be able to get some insights into that if we have a multi-dimensional RD design. So what is a multi-dimensional RD design or MRD design? I am using this to refer to cases where treatment is determined not by a single running variable, but more than one. And for simplicity in this talk, I'll assume just two, and I'll call them X1 and X2. As an example, financial aid eligibility for students often depend on not only academic performance, but also family income. So we have two running variables. A big difference from single-dimensional RD designs is that the threshold in a multi-dimensional case is no longer a point, as like you see in the left figure for single-dimensional RD designs, but it is a frontier. So in the right figure, we see that the threshold is basically the positive x1 and x2 axes, the bolded parts of the axes. And because of this feature of the multi-dimensional RD design, we are actually able to estimate heterogeneous treatment effects for any points along this treatment frontier. Here's a visual illustration of the MRD design. And here we have an application actually drawn from the empirical application I'll go over later, where we are interested in the effects of financial aid on college going. So on the X1 and X2 axes, we have the two running variables, test scores, and the inverse wealth index. And the outcome variable is the vertical axis. The vertical gap between these two surfaces, this basically the CEF for individuals who are eligible for financial aid and the CEF for those who aren't. The vertical gap between these two surfaces is treatment effects. And we can actually see from this graph that the treatment effects seems to be slightly decreasing. So first of all, it is positive. So financial aid seems to encourage more people to enroll in college, but the treatment effects is smaller for students with exceptionally high test scores. Whereas maybe it's not totally clear from this graph, but the treatment effects is roughly constant as a function of family wealth. Now, the thing about applied work with MRD designs is that most of them do not take advantage of this feature of the MRD to estimate heterogeneous treatment effects. Instead, typically what they do is they limit the sample to individuals eligible on one dimension and estimates a single dimensional RD on the other dimension. So again, if we go back to this figure in the bottom right here, they might throw away individuals falling below zero on the X2 axis and focus on a single dimensional RD using X1 as a running variable. Or separately, they may throw away individual with X1 values below zero and focus on a single dimensional RD using X2 as the running variable. So when they are doing that, they are basically estimating an average effects over the two segments of the treatment frontier separate. So there are a couple of disadvantages of this applied approach. First of all, it does not make full use of heterogeneity. For example, we can't answer questions such as is the treatment effects increasing or decreasing in income or test scores. A second disadvantage is that it is quite inefficient. Specifically, it throws away a part of the sample, which is actually often a very large part. So we'll get larger standard errors. In today's talk, I'll describe a simple and more efficient way to estimate MRD designs, which also allows us to estimate heterogeneous treatment effects. So with the growing availability of richer datasets, MRD designs can be used in an increasing number of settings. In the previous example, we saw that financial aid may depend on academic performance and family income. Another example is Medicaid eligibility, which in some states depends not only on wealth, but also on the age of the individual. And finally, another example is going back to the example on newborns. Extra attention is not only paid to very low birth weight individuals, as we saw that was the RD that Elma et al. Used, but it also depends on whether the baby is classified as premature, and that's usually defined as a gestation age of less than 37 weeks. So again, we have two running variables and a potential MRD design. Okay, so that's all for the introduction. Are there any questions I should address at this point? Okay, so I'll move on for now, but feel free to interrupt me at any moment if you have any questions or comments. So in this next section, I'll talk a little bit about the theory on MRD estimation, but I'll go over it at a high level and focus more on intuition rather than econometric details. So here's just how I am defining. Here I'm just defining the MRD estimate, and there's a bit of notation, but basically it's the same thing as the single dimensional RD design. We are estimating the difference in the CEFs at the threshold. So going back to this figure, we are taking the difference as we approach a threshold from the treated site versus the untreated site. And then the difference is the MRD treatment effects. So how do we estimate it? First, we need to estimate the CEF, the conditional expectation function of outcomes as a function of the two running variables in the region of the running variable space where individuals are eligible for treatment, and another CEF in the region of the running variable space that individuals are not eligible for treatment, and then we'll take the difference. So this sounds simple, but the question now is how to estimate these surfaces in a sensible way. So before talking about how we do this for MRD designs, let me first talk about how people used to do it for single dimensional RD designs and some of the intuition for what type of estimation method it will be sensible should carry over. So a common approach in applied work for single dimensional RD designs in the past is to simply fit global polynomials on the two sides of the thresholds. For example, people have fit like quartic polynomials and just taken a difference at the threshold. Econometricians have made the point that this is typically not a good idea because the estimates of the treatment effects at the threshold may be affected by observations that are very far away from the threshold. This is especially the case if you use a high order polynomial, because these polynomials tend to be quite wiggly and they tend to have what they call quote unquote waggy tails. So the estimates at the boundary may be quite sensitive to observations that are quite far away from that point. And that's not what we want in an RD estimates, because in RD estimates, we are essentially only interested in observations very close to the threshold. So instead of global polynomials, econometricians suggest using local linear regressions. And most applied work nowadays actually adopts this practice now. So what are local linear regressions? They are basically a non-parametric estimation method, which utilizes only observations very close to a point when fitting that point. There are also theoretically optimal properties of local linear regressions in the RD setting, and that's why people use it mostly use it nowadays for single dimensional RD designs. As with most non-parametric estimators, we need a way to regularize it, which is basically a way to control how wiggly the function can be. Because if we allow it to be arbitrarily quote unquote wiggly, then it'll basically perfectly fit every point, and that is usually not a good idea because we don't want to overfit. Now, the tuning parameter in local linear regressions is something called a bandwidth, and we want to choose a bandwidth that balances both the bias of the estimates and the variance of the estimates. So basically, how people choose a bandwidth is typically to minimize the mean squared error. And we'll call the bandwidth that achieves this the optimal bandwidth. There's a formula for the optimal bandwidth for local linear regressions, but it is quite complex and it depends on parameters like the second derivative of the conditional expectation function that will also need to estimate on parametrically. So it is not that straightforward to estimate, but people people do it for the single dimensional case. Now, moving on to MRD estimation, an idea is to simply extend local linear regressions to multiple dimensions. So can we do this? Should we do this? In principle, we can do this, and econometrically, it'll have some theoretically optimal properties. But in practice, the data requirements will be very, very high. And to explain why, let's return to this figure where I have the treatment frontier, which is the threshold in multiple dimensions, bolded. Remember, in the single dimensional RD case, you needed to estimate an optimal bandwidth at a single point at the threshold, but now in a multi-dimensional case, you basically need to estimate a continuum of optimal bandwidth. So an optimal bandwidth at every point along this treatment frontier. So this is going to require a lot of data. And secondly, the optimal bandwidth in multiple dimensions is also more complicated. Specifically, we'll need to estimate the Hessian matrix, which is basically the second derivative in the two-dimensional case. This is unlikely to work well if we don't have a lot of data. So to recap, what we want in a good estimator in the MRD case is first, it should be flexible. So estimates close to the treatment frontier should not be affected by points very far away. Second, we don't want it to be too flexible. We don't want to overfit. So we need to control the smoothness of the CEF somehow. And finally, we would ideally want the estimator to be feasible and easy to compute. And that is basically the main pitfall of estimating MRD designs using local linear regressions, and the reason why I'll be focusing on a difference estimation method. So the solution I propose is to use another non-parametric estimator called thin plate splines. And here I have a definition of thin plate splines. Basically, it's the function that minimizes this quantity, which is basically a combination of the squared loss as well as a penalty term. And this penalty term has to do with the second derivative of the function. So functions that are more wiggly, that have more curvature, are penalized more. And there's this penalty parameter, lambda, which basically controls how smooth the function should be. Now there's well-established routines for computing the mean squared error optimal penalty parameter lambda for thin plate splines. And the biggest difference with local linear regressions for our purposes is that this penalty parameter or regularization parameter lambda, it is a scalar, whereas the penalty parameter for the local linear regressions is not a scalar, but it is a continuum. So in this figure, I just need to estimate a single penalty parameter lambda instead of a different lambda for every single point. So it is much simpler to estimate than local linear regressions. So I estimate two surfaces and take the difference using estimate two surfaces using thin plate splines and then take the difference, estimate true inference estimates. Now, how do I conduct inference? The simplest method is to construct Bayesian standard errors. So if we choose suitable priors for the thin plane splines parameters, it is easy to construct Bayesian confidence sets. Or alternatively, we can simply use non-parametric bootstrap to obtain standard errors. So in each iteration of bootstrap, draw with replacements observations from the original data set and then estimates MRD treatment effects for each iteration, and then in the end take the standard deviation of those range of bootstrap estimates. Now there is a potential issue with inference when we are using mean squared error optimal estimates. And this is not a problem specific to my method, but is actually quite general for all non-parametric methods. Specifically, when we are computing mean squared error estimates, we are trading off variance and bias of the estimator. And usually, because of this trade-off, in the end, we'll have non-zero bias. So in the asymptotic distribution, there will be non-zero bias. And this can complicate inference because you can imagine if the treatment effects estimates is not centered at the true treatment effects, even if the standard errors are correct, the coverage rates of the 95% confidence interval may not be correct. So the solution I adopt here is use undersmoothing, and I have two methods for doing so, which I'll not go through in detail unless anybody has specific questions or is particularly interested in this. But basically, the idea is to use a penalty parameter that is larger, so larger than the MSE optimal penalty parameter. And when I do that, basically the bias will be quote unquote negligible in the asymptotic distribution, and we can conduct correct inference. So that's all for the theory. Any questions at this point? Okay, so now I'll move on to some simulation results to see how this MRD estimator does. So basically, I'll be comparing its performance with a number of commonly used single-dimensional RD methods. The true data generating process will be based on a fifth-order polynomial, and I will have two specifications. In one specification, we have constant treatment effects. So the treatment effects is constant along the treatment frontier. In the second specification, I'll consider heterogeneous treatment effects, where the treatment effects is increasing in one running variable and decreasing in the second. For each simulation, I'll be conducting 100 simulations. So for each specification, I'll be conducting 100 simulations, and I'll have 10,000 observations in each simulation. So here is a plot of the DGP, the data generating process, when we have for the constant treatment effects case, and we can kind of see that the vertical gap between the two surfaces are pretty much constant. So here is a table showing the simulation results, and there are two panels which basically correspond to the two segments of the treatment frontier. So one panel basically corresponds to your average treatment effects over this part of the frontier, and this other panel corresponds to that part of the treatment frontier. Now, for the MRD estimator, I can also easily consider the average treatment effects over the entire frontier, but I'll focus on the two segments because this is basically what the single-dimensional RD methods do, and I want to compare the performance of my estimator to those. Okay, so the first three rows in each panel are various single-dimensional methods, and the last three rows are various ways of using my MRD estimator, basically as different settings, and I'm just testing each one. So we can see in the first column that the MRD estimator has a little bit larger bias in some cases, but the bias is still relatively small, and instead it has a lower mean squared error than the single dimensional cases typically. And actually all of the methods tend to have pretty much accurate coverage. And finally, the confidence intervals lengths for my MRD estimator are slightly narrower, so the standard errors tend to be smaller. So I guess the main takeaway from this panel is that when we are interested in like constant treatment effects, my MRD estimator performs comparably with single dimensional methods. So perhaps slightly higher bias, but smaller mean squared error and smaller standard errors. Now let's consider the second data generating process with heterogeneous treatment effects. And here we can see quite clearly that the treatment effects is increasing in X1, and it seems to be decreasing in X2. So I did mention earlier that single dimensional methods are not suitable for estimating heterogeneous treatment effects. But for these simulations, I forced them to estimate heterogeneous treatment effects by using thin slices of the data. So to describe exactly how I estimate heterogeneous treatment effects using single dimensional methods in these simulations, suppose that we are interested in estimating the treatment effects at this single point that my cursor is at. So some points where X1 is 0 and X2 is equal to this positive value. If I really want to use single dimensional methods to estimate the treatment effects at this point, I will basically use a slice of the data, basically imagine two horizontal lines that bracket this data. I'll use only observations in that thin slice to estimate a single dimensional RD. And the treatment effects using that thin slice of data will approximate the treatment effects of interest. So what happens if I do that using a single dimensional methods? Basically, if we look at the first three columns, we see that the coverage rates tend to be quite low. So the coverage rates of the 95% confidence intervals is only around 75% in in panel A, and slightly above 50% in column B. What this tells us is that estimating heterogeneous treatment effects using single dimensional methods probably doesn't work well and will need a lot of data, so much more than I'm using in these simulations. Now, if we compare that to the MRD estimator that I'm proposing, the MRD estimator has smaller integrated mean squared error, higher coverage rates that are quite close to 95%, and actually much smaller, much narrower confidence intervals. So it is both more precise and has higher coverage rates. Okay, so those are the simulation results, and basically the takeaway is that it really outperforms single dimensional methods if we are estimating heterogeneous treatment effects. And also, even if we are only interested in constant treatment effects, it tends to be more precise. So next, I will be covering empirical applications, but before that, I just want to pause again to check whether there are any questions from the audience. Okay, I guess I'll move on. So I'll be covering two empirical applications. The first one I already described briefly just now. This is basically an empirical application from an education setting, specifically the effects of financial aid on college enrollment. But we can imagine how this can also easily apply to study healthcare-related questions. For example, if we are interested in the effects of college going on later life outcomes, we can basically use a fuzzy MRD design. So in the first stage, we can look at the effects of financial aid eligibility on college enrollments. And for the reduced form, we can estimate later life health outcomes and look at the effects of financial aid eligibility on that outcome, and then take the ratio as is standard in IV settings. But let's go through this example first. So the effects of financial aid eligibility on college enrollments. As I mentioned, students, so this is actually a setting from Colombia based on the study by Juliana Londono-Velez and co-authors. So students in Colombia are eligible for financial aid if their test scores exceed the threshold and family wealth is low enough. So we have an MRD design here where the test scores and an inverse wealth index are the running variables. And we'll use this to study the effects of financial aid on college enrollments. Now, before estimating the MRD design, I'll test the identifying assumptions. So the first test, recall that in a single dimensional case, there is something called a Macquarie test, and we can do something very similar in multiple dimensions. So basically, we want to test whether the multivariate density function of the running variables is continuous at the threshold, at the treatment frontier. So a simple way we might do this is to actually just plot two univariate histograms. So a histogram for x1 and a histogram for x2, and see whether there seems to be a discontinuity at the threshold. However, this is technically, it's not the best we can do, because it is possible that even if the single dimensional histograms look continuous, there is actually discontinuity in the multivariate distribution. So basically here, what I've done is to extend the Macquarie test to multiple dimensions. And here, I've plotted the estimated discontinuity in density for the two segments along the treatment frontier. So what we want to see in a valid MRD design is that the estimated discontinuity in the density function along the treatment frontier is close to 0 or not statistically different from 0. And here the dark gray regions correspond to the points-wise confidence intervals, and the light gray regions correspond to the simultaneous 95% confidence bands. And we can see that along the two segments of the treatment frontier, the estimated discontinuity is not statistically different from 0. Okay, so that's the first test. The second test is to conduct placebo RDs. So recall that we are basically estimating an MRD design with a predetermined characteristic as the quote-unquote placebo outcome. So again, if students are not able to precisely manipulate the running variable and sort to the exact side of the threshold that they want, we should see that there is no treatment effects when we use these placebo outcomes. So here are the results where I use age as the placebo outcome, and we can see that the treatment effects estimates are not statistically different from 0 along the two segments of the treatment frontier. And here I've done the same using gender as the placebo outcome. And again, we see that it is the treatment effect estimates are basically not statistically different from 0. So it looks like we have a valid RD. So let's now show some results. The first thing I'll do again is to compare my MRD estimates to estimates using the single-dimensional methods. And in particular, I'll compare it to the original estimates from the paper by Londino Velez et al. And here we have the results along the test score threshold. So one of the two segments of the treatment frontier. And I'll not go over the numbers in great detail, but basically we get the same qualitative results. The points estimates are quite similar. But if we look at the standard errors, the MRD standard errors tend to be a little bit smaller. So like 0.007 compared to 0.011, 0.005 compared to 0.009. Now, if we look at the results from the other threshold, again, the points estimates are qualitatively similar. But actually, the difference in standard errors is much greater now. So in some cases, we see that the MRD estimator standard errors are less than 1/3 of the standard error from the original paper. For example, here we see that the MRD standard error is 0.005, original standard error is 0.018. And why is this a case? We can really, so the number of observations really tells us a lot. So you can see that MRD estimator uses pretty much an entire sample, which is almost 350,000 observations. Whereas the original paper, when it's looking at the well threshold, only uses 23,000. So this is because they are throwing away individuals whose test scores make them ineligible for financial aid. And actually in this setting, the test score threshold is very high. So they end up throwing away more than 90% of their data. And that's why the standard errors are much larger. Okay, so finally, here I have results on treatment effects heterogeneity, which is, I think, the biggest value added of the MRD estimator I'm proposing. Here I've plotted the treatment effects along the two segments of the treatment frontier. In the first plot on the left, we see that the test score seems to be decreasing the treatment effect seems to be decreasing as a function of the test score. Whereas in the second plot, we see that it doesn't seem to change systematically with family wealth. So this is actually so the fact that the treatment effect is decreasing in test scores is not a priori something that is obvious. In particular, in the education literature, there has been findings of a quote-unquote reverse Roy effect. So an example of this is Klein and Walters. They have a paper studying the effects of Head Start. And what they find is that students whose returns to education are basically the highest are also typically the least likely to take up additional education. And if that applies to this setting, then we might actually expect the direction of the treatment heterogeneity to go in the opposite direction. Because perhaps the highest ability students whose returns to college are the highest, they are really the ones who require the additional financial incentive to enroll in college. But actually we see the opposite here. And one possible reason why this is the case is that for the highest ability students, even without the program, even without financial aid eligibility, enrollment in college is already quite high. So there's a ceiling effect. So I guess the takeaway from this is that the MRD estimator allows us to estimate heterogeneous treatment effects. And this can allow us to answer economic questions or questions that policymakers might be interested in. And the answers to this question are not a priori obvious without conducting this exercise. Now, in the second empirical example, I'll cover a geographical MRD design. And this particular example comes from a political science study, but we can imagine other potential applications of geographical RD designs for health research, including there was a paper that used a time zone RD to look at the effects on health. Now, in this particular application, the authors were interested in studying the effects of campaign advertisements on voter turnouts in the 2008 US presidential elections. Political campaigns buy TV adverts based on designated market areas, DMAs, which are chosen by the Nielsen Media Research. And the authors argue that precise DMA designation is unrelated to political variables. So what we're doing here is to use an MRD design exploiting the fact that neighboring DMAs receive very different levels of TV presidential advertisements in the lead up to elections. In particular, on one side of the DMA border, voters received an average of 177 daily adverts, whereas on the other side of the border, voters received no adverts at all over this time period. So here's just to show you how it looks like geographically. I actually forgot whether the blue or the red is control and treatment, but basically the X and Y axes here are the longitude and latitude, which are our two running variables. And the treatment frontier is no longer a right angle like we saw in those previous examples, but it is this black curve that separates the two bordering DMAs. So what we are essentially doing is comparing observations like the blue ones that are close to the bordering, to the boundary, to voter turnout in the red ones that are also close to the boundary. So here I've plotted my MRD estimates in black and gray, and I've shown how it varies along the entire treatment frontier, along the entire border. And actually the authors in one of the previous studies looking at this, they also developed a local linear estimator, which can be used to estimate heterogeneous treatment effects. And they actually do this by collapsing the two running variables, longitude and latitude, into a single running variable, which is distance to the boundary. And what they are doing is actually kind of similar to what I was describing in the simulation example just now, where we are trying to use the single dimensional method to estimate heterogeneous treatment effects. Basically, they are weighting observation. So if they are interested in studying the treatment effects at a particular point at a boundary, they have this kernel function that weights heavily observations that are close to this point. So points that are further away from this point basically contributes nothing to the treatment effects at this particular point. And what we see first with my MRD estimator is that it tends to be quite stable, and at any point along the boundary, we cannot reject the null hypothesis that the effects of campaign efforts on voter turnout is zero. And this basically replicates the findings, the original study's findings. However, if we look at the local linear regressions, we see that in some cases, at certain points of the boundary, it is very unstable. So here we see that there's actually a treatment effects estimates of more than one, which is like economically not possible, where because our outcome variable voter turnout, like based on the definition of the dependent variable in this setting, voter turnout, which is a dummy variable, and we of course have a dummy variable for treatment as well. So treatment dummy, outcome dummy, you can't have a treatment effects greater than 1 or smaller than -1. So basically, because of the small number of observations used for each local linear regression at each point, the estimates can be quite unstable. So that was also kind of what we saw in the simulations earlier. Okay. Before I go on to extensions, any questions about empirical applications or anything? Okay, so we still have some time remaining. So I'll cover a couple of extensions to the multidimensional RD design. The first of which is regression kink designs. So again, let me describe the single dimensional case. The difference between regression kink or RK designs and RD designs are two. So first, the endogenous variable Wi is continuous in the RK design. And second, instead of leveraging a discontinuity, as in the RD design case, we are leveraging a kink in the in the CEF. So this sentence is actually not exactly accurate. It's not a kink in the first derivative, it's a kink in the CEF, and that will actually result in a discontinuity in the first derivative. So that's what we are exploiting here. So a typical example is unemployment insurance. And in many cases in the US, for example, in Louisiana, the replacement rate, or basically how much it should say the UI benefits, WI, is a fraction of previous income. So let's assume alpha times previous income X. But this only increases linearly up to a cap. And after this cap, so assume that the maximum cap is alpha times X bar. Even if your previous income goes even higher, the UI benefits just stay constant after that. Makes sense because you don't really want to pay millions of dollars to unemployed CEOs in UI benefits. So what this results in is a kink at X bar. And the RK basically can estimate the effects of additional UI benefits on some outcome of interest, which is often like job finding probability. And the way they do this looks actually a lot like the fuzzy RD design, where we take the ratio of the difference in CEFs for the associated outcome and associated with the treatment variable. But instead of the CF of the outcome, we are looking at the first derivative. So the discontinuity in the first derivative of job finding probability divided by the discontinuity in the UI benefits formula in the denominator. Now, we can imagine multidimensional extensions of RK designs. So first, and again, this is actually based quite closely on the Louisiana's UI benefit system. So this is actually a potential setting where we can use this design. So suppose that the cap used to stay at the same level for some time, but at some time t0 onwards, the cap is gradually raised. So assume that is raised like perhaps every year or every quarter. So it becomes higher and higher. Then in this case, we have a kink not only at x bar and t and time prior to t0, but also another kink at the higher cap at times after t0. So we can, I actually have an RD package, I should have mentioned it earlier, that covers not only MRD designs, but also multidimensional RK designs. And but anyway, the RK estimate, this should say the MRK estimate, basically looks a lot like the single dimensional case, except that here we have a directional derivative instead of just a derivative for univariate functions. So why would we want to use MRK design? Again, it could be because we're interested in treatment effects heterogeneity. For example, we might be interested in whether the effects of a marginal dollar on UI is greater or smaller when UI is more or less generous. So perhaps that was a little bit, the description was a bit wordy, but here I have a visual illustration of the setting I just described. So on the left, we have UI benefits as a function of time and prior earnings. And here we can see there are actually multiple kinks. So here we have the kink prior to the unemployment formula being gradually raised. We also have a kink here. And yeah, if we look at the right figure, which shows the job finding probability as a function of the two random variables, time and prior earnings, we see corresponding kinks in the outcome response surface. And it may take a few minutes to actually orient yourself with these figures. But what these patterns show is that UI benefits has negative effects on job finding probability. But this particular example is based on simulated data. I don't yet have an empirical application for this. Okay, and finally, let me go over briefly multidimensional regression discontinuity / kink designs. So I'll call this MRDK designs. So as an example, consider again the setting we just had with UI benefits, but instead of a gradual increase in the cap at time t0, suppose that there is a one-time increase in the cap to a higher value, so alpha x star. Now we have a kink as before at x bar prior to t0, but we also have a discontinuity for for prior earnings between the previous value associated with kink and the new value. And this discontinuity occurs at time t0, at the time of the policy change. So visually, what this looks like is this. So you can see that there's the kink as before, but here at the time of the policy change, t0, there's a discontinuity in benefits. And what this means is like if your prior earnings was like in this range, between X bar and X star. If you applied for UI slightly before the policy came into effect and applied slightly after it came into effect, there is actually a discontinuous jump in your UI benefits. Now, if this was an empirical application, we may actually be worried that perhaps if people knew that this policy change was coming into effect, they might slightly delay their application for UI benefits so that they can get this higher benefits level. But again, that is something we can check using like the multidimensional McCrary tests or using the placebo RD methods that I covered earlier. And in this right plot, we see that there's also a corresponding kink and a corresponding discontinuity when we look at job finding probability as a function of prior earnings and time. So that's how the MRDK design works. So to conclude, today I introduced multidimensional RD designs. I provided a simple estimation procedure that allows users to recover heterogeneous treatment effects. And it also improves precision relative to single-dimensional methods that applied work have previously used when encountered with multidimensional RD designs. I also covered extensions of this method to multidimensional kink designs and also MRDK designs, which are a combination of multidimensional discontinuity and kinks. And finally, there are many potential applications in healthcare research. For example, we can use this to study the effects of Medicaid, the effects of medical spending on at-risk newborns, and the effects of education in health. So if you have any questions after this, feel free to email me, and the paper is also available on my website if you're interested in any details. And finally, if you're interested in using this method for anything, I also have R code for estimating MRD and MRK designs on this GitHub page. So thank you for your attention, and I hope to answer some questions if you have any. Okay, so there's a question about, is MDRK design appropriate when the data is censored? So I am assuming this is asking about when the outcome variable is censored. If that is the case, I think there will be, so as with like normal, like ordinary squares regression with censored data, there will be some issues, but you could, but there are ways with dealing with that. So, for example, if you're interested in like the effects of some policy on income, and then the income data is censored, perhaps you could define, instead of using income as your outcome variable, you could define a dummy for like very high income, or like perhaps income above like a certain value. You can like deal with this censoring issue using other methods like this. If you are talking about running variables being censored, so I'm assuming like very like large and small values of the running variables are probably like assigned a particular value. That shouldn't matter, because like for RD and RK designs, only observations that are very close to the threshold are used for ideally are used for estimation. Yeah. I think Owen also has a question.
Yes, thank you very much, Alden. That's extremely useful to get that overview and this introduction to this exciting new methods. I think it's fantastic the research you're doing here. So well done indeed.
Thank you.
So I had one question about so in your simulations, if I understood correctly, perhaps you could help me just to get to intuition of one of the results, because I understood, perhaps I got it wrong, but I understood in the case where there is no treatment effect heterogeneity, so the simple case, and in the case where in one of the dimensions you're using almost all the observations, so there's not a big difference in sample size between the MRD and the single dimension RD approaches, your approach was still doing as good as or even better than the univariate. And I didn't quite understand why in that case, because I was thinking, well, in that case, you're sort of not losing too much. The univariate can't be going too wrong because there's no heterogeneity. And then perhaps it's got an advantage because it can optimize better with the bandwidth to sort of deal with that, whereas you've not got that in your method. So why in that case does your method do so well?
Yeah, thanks for a question. I'm assuming like you're talking about this example, this simulation.
That's
with,
right, yes.
Yeah. So first of all, the univariate methods are still throwing away like half of the data for each dimension. So like if they're estimating this particular gap here, they are throwing away observations with like x2 smaller than 0. So they are pretty much only using half the sample size that I am. But then sample size itself isn't really necessarily a very like best measure here, because like with non-parametric methods, my estimates of this particular gap only really depend on observations close to it. But I think it's a little bit of a mixed bag. I wouldn't say it's like strictly better, because like my estimator tends to have higher bias. And I guess that is kind of owing to like there are some shortcomings of thin plate splines, which is that they can be a little bit unstable at their boundaries. Whereas like local linear regressions, there are some theoretical results showing that they are optimal for like boundary bias issues. So it does suffer a bit on bias, but if we look at like mean squared error and also standard errors, it tends to be like my estimator seems to do slightly better. I'm not sure if that totally answers your question. Does it?
Yeah, I missed the bias part a bit. Yeah, you're right that it's doing a little bit worse on the bias perhaps. Well, sort of related to that perhaps. So I was wondering, so in your method you have with the thin space spline, you have this single a penalty parameter.
Yes.
And so I was wondering, so one might think that in some way that's sort of restrictive, that you're imposing. So I'm understanding that you're imposing like there's one penalty parameter in both dimensions of the space. If that's correct, then could you make your method just a little bit less restrictive, a little bit more by allowing for like 2 penalty parameters? Would that be a sensible way to go, or?
Yeah, that is a possibility. I think there is some like statistical work that has tried to relax this this restriction for thin plate splines to allow the penalty parameter to vary. But I guess it's kind of a trade-off, right? So like simplicity and feasibility versus like for local linear regressions, you have like an infinite number of like tuning parameters that you can work with. So like theoretically, you can certainly do better, but in practice, you may need a lot of data to actually achieve those improvements. Let me think about this. So I guess one concern, like you said, is like there are two dimensions, two running variables, so maybe you want two tuning parameters. Perhaps like empirically, like for applied work, what might be good practice? Actually, it's also good practice for like a lot of like machine learning and parametric stuff. Is that you may want to standardize your two running variables. So like hopefully you don't have like the scale of one of the running variables being in like the millions and the other running variable being like between like less than one, like in magnitude. So perhaps like standardizing both running variables would also help with the estimation procedure.
Yeah, definitely. I think. Okay, thank you very much. Thank you.
Sure, thanks. Okay, so yeah,
thank you very much. So we're having a few minutes time, maybe 3-4 minutes. So if you're having any more question, please feel free to make some interaction. Thank you then again for participating in this webinar of Health Systems Efficiency Group of International Health Economics Association. If you're having any suggestions, comments, feedback, please feel free to write to us. Alden, thank you very much for making us enlightened with your new approach. Hope to see you soon again. We conclude the session now.
Yeah, thank you. Thanks for coming.